Today I'll be talking about LoRa low-rank adaptation of large language models. Adapting one large-scale retrained language model to multiple downstream applications has gained more and more attention. Such adaptation is done through fine-tuning, which updates own parameters. When models become larger and larger, more than 100 billion parameters, such adaptation becomes critical deployment challenge. There are many attempts to address this challenge by either adapting only some parameters or learning external modules for new tasks. The issue of current methods are they introduce inference latencies and they fail to match fine-tuning baselines. This study hypothesized that chain weights during model adaptation has low intrinsic ranks. In other words, only a subset of weight matrices in retrained model should be updated during the adaptation. So the goal of these studies is to propose an effective adaptation strategy that introduces no inference latency and retains high performance quality by optimizing low rank decomposition matrices of dense layer chains. In LORA, retrain width W are frozen. Goal of adaptation is to learning task-specific updates delta W. The task-specific updates are projected to lower dimension using low-rank metric decomposition. So delta W is represented as the multiplication of two smaller metric B and A. During adaptation, the low-rank approximated matrices A and B are learned. The key advantage of LoRa are the pre-trained model can be shared to build small LoRa models for different tasks. Replacing matrices A and B efficient, which reduce storage requirement and thus switching overhead significantly. When a full large language model can take 10 to 20 gigabytes of spaces, reduce GPU usage during training. In the experiment, authors observed that LoRa reduced to two-thirds VRAM consumption during training. It also reduced the checkpoint size 10,000 times. And they also observed 25% speed up during training, as we do not need to calculate the gradient for the vast majority of the parameters. LoRa also introduced no inference latency compared to fully fine-tuned model. LoRa can be combined with other methods, such as prefix tuning. In this next section, we'll present the main results of the experiment on this paper. In principle, we can apply LoRa to any subset of weight matrices in the neural network to reduce the number of trainable parameters. In this study, LoRa is only applied to attention weights of transformers architecture. Adapting MLP layers, layer norm layers, and biases are our scope. The authors evaluate adaptation performance of LoRa on pre-trained Roberta, DiBerta, GPT-2, and scaling up to GPT-3, 175 billion. The authors evaluate wide range of downstream tasks from natural language understanding to natural language generation. They compare LoRa to different baselines. Fine-tuning art is where we on pretend widths are updated. Another simple variant of fine-tuning is to update the last two layers. Another baseline bias only or bit fit only bias vectors are updated. Another baseline is prefix embedding tuning, where we insert a special token, special tokens among input tokens. These special tokens are tunable with embedding. An extension of prefix embedding tuning is prefix layer tuning, where we learn activation after embedding layers for some special tokens. And finally, adapter tunings, where we insert adapter layers between self-attention module and subsequent residual connection. In this slide, we compare inference latency of fine-tuned LoRa methods to widely used adapter methods. The table shows inference latency in milliseconds of the methods. Adapter layers are designed to have fewer parameters using small bottleneck dimension. However, adapter layers need to be processed sequentially, while large neural networks rely on hardware parallelism to keep latency low. This makes a difference in the online inference setting, where batch size is typically as small as 1, and we see in the last column of the table. And we can see that there's this a noticeable increase in latency when using adapter compared to full fine-tuning model or LoRa. This slide presents performance in different adaptation methods on different natural language understanding tasks include benchmark. The higher the score, the better it is. LoRa tends to match fine-tuning of Roberta-based LART and DBERTA. This slide presents performance of different adaptation methods on natural language generation in different metrics. The higher the score, the better it is. And LoRa tends to match fine-tuning of GPT-2 on natural language generation. Finally, the authors scale up the pre-trained model to GPT-3 175 billion parameters. The table presents performance of different adaptation methods on 3 evaluation sets. And LoRa matches or extends the fine-tuning baseline on all 3 datasets. The question is, what is the optimal rank for LoRa is? The table shows performance of different ranks on 2 evaluation datasets. Surprisingly, LoRa performs competitively with a very small rank. This suggests update metric delta W would have very small intrinsic rank. In conclusion, this study proposed LoRa, an efficient adaptation strategy that introduced no inference latency while retaining high model quality. And it allows quick task switching when deployed as service by sharing vast majority of model parameters. Thanks for your attention.